Today's topic is on the image restoration using Weiner filtering. And before we go over to this topic, let us recapitulate what exactly we did in the last one or two classes. Now, primarily, we had considered a degradation model, and we had formulated the degradation model in the discrete domain, where we had obtained the relation like this, that the degraded image G in the vector form can be written as product of HF plus n vector, okay, where F happens to be the original image, okay, that is the pre-degraded image rather, then H happens to be a block circulant matrix indicating the impulse response of the degradation model, and N is the noise term which is present. All right. Now, the problem was that if somebody gives us G, okay, that is to say the degraded image, then we have to make an estimate of the original image, okay, undegraded image, which we will call as F hat, okay. And we had said that we are going to make an estimate of this F hat such that we can minimize the squared error between G and H F hat, okay. So we had considered the minimization of this form, G minus H F hat, this term square, the norm of this square, okay, and we were going to minimize this, which we had equated to a noise term N. All right. Now, we had also seen some very interesting properties related to the degradation model, and especially about this degradation function H, okay, which is the first interesting property of that is it becomes a block circulant matrix, okay, which we pointed out in the last class. And the second thing is that it can be very nicely diagonalized, okay, and we saw that how it can be diagonalized by pre-multiplying it by W and post-multiplying it by W inverse, where W happens to be the Fourier transform kernel, the vector indicating the Fourier transform kernel. And going by that, okay, we had obtained some interesting results. For example, we had considered minimization of this expression, okay, which actually led to the relation like this, that we can obtain by minimizing this, okay, we can obtain F hat as H inverse G, assuming that H inverse exists. All right. And by considering this expression, all right, that F hat becomes H inverse G, we had considered the inverse filtering, in which case we had obtained the relation in terms of the Fourier transform coefficients. So what we got was, in the Fourier transform domain of the estimated image, which we are calling as capital F because it is in the Fourier domain and its coefficients are KL. So the KLth Fourier coefficient of the estimated image was given as, from this H inverse G, we had obtained this thing as the GKL, okay, sorry, GKL divided by H of KL, okay, and this was our inverse filtering result. We had obtained that, you know how we had obtained, by pre-multiplying the left hand side as well as the right hand side by W inverse, and by looking at the physical interpretation of the different matrix components that we got in the process, and this is what we had got as inverse filtering. And we also pointed out certain limitations of the inverse filtering, because if at some KL, HKL becomes equal to 0, then we can't calculate this F hat of KL at that particular point. That was one of the major limitations, and we also discussed that how we will circumvent that limitation by going over to pseudo inverse filtering. Okay, in which case we had said that if HKL, okay, if at any particular point HKL becomes equal to 0, then at that point we will keep f hat of KL also equal to 0 and obtain otherwise if HKL is not equal to 0, we will make use of this relation, and exactly that is what we talked of, okay, in the last class. Now basically one point which we had considered was that we had considered minimization of only this particular term, okay, and this was nothing but an unconstrained minimization, okay. So what we had considered last class was an unconstrained, you can call this as an unconstrained regression problem, in which case f hat is obtained simply as H inverse of G, okay. Now today we are going to consider minimization under constraints, okay, and let me tell you how are we going to do that. In the case of constraint minimization, okay, or in case of constraint restoration rather, we are considering the minimization of the form QF hat, okay, norm of QF hat square, okay, where Q is nothing but where Q is a linear operator on F, okay. Q is a linear operator, consider any linear operator, okay, and if we operate f hat on Q, okay, then the norm that we get Q f hat square, okay, we are going to consider minimization of that subject to the constraint, same constraint which we had discussed earlier, that is to say minimize this, okay, minimize Q f hat square, okay, subject to the constraint norm G minus HF hat square equal to norm n square, okay. So in earlier case we were minimizing this expression, all right, and now what we are going to do, we are going to minimize QF hat square subject to the constraint of this. So this we are now putting as a constraint. In earlier case we were putting as an unconstrained problem by directly minimizing this, and now we are formulating it into a constrained problem where we are minimizing QF hat square under the constraint G minus HF hat square equals to n square, all right. So that means to say, okay, in our objective function that we are going to minimize, we are going to consider the term containing QF hat square as well as the term containing this error, okay. Let us see that how exactly we are formulating our criterion function. Criterion, or rather the objective function, is now defined as follows: J f hat, okay, because after all we are going to minimize with respect to what? Again with respect to f hat, because our ultimate problem is to have a good estimate of f hat, all right. So the objective function written in terms of f hat, okay, is as follows: Q f hat square, all right. This term obviously we are going to minimize, okay, plus we are going to introduce the constraint term, okay, with some multiplication factor, okay. So let us have some multiplication factor alpha, okay, and then we are going to consider within this parenthesis we will be writing the error in the constraint term. And what is that? So that means to say, since this is our constraint G minus HF hat square equal to n square, this is going to be our constraint, obviously we are going to consider the error G H minus F hat square minus n square, okay, as the error term, which we will multiply with alpha and add it with the Q F hat square, which we anyway have to minimize, all right. So this is Q F hat square plus alpha G minus h f hat square minus n square. All right, this is what we are going to minimize. So our problem now is to minimize this entire expression. If we can minimize this, okay, obviously we are minimizing this under this constraint. Now you can as well ask me that why at all we are going in for this formulation. Wasn't the earlier restoration problem good enough? Earlier we had considered minimization of only this, okay, and now why I am going in for this? Well, the advantage that we are getting in this process is that we can generate different solutions, okay, in this case, because we have this Q under our control, okay. So this gives us a much more flexible image restoration, okay. So obviously we can tune this Q, we can also tune this parameter alpha, all right. So we have now used the minimization function in a much broader sense, such that it gives us much more flexibility than what we had in the unconstrained restoration problem. So minimization, so the image restoration which we will get by minimizing this expression, we will call that image restoration as a constrained restoration. So if I solve this, I will be doing what is known as a constrained restoration. All right. Now how to minimize this? Okay. Now again, coming to this term alpha. Actually alpha, as I already told you, it is a constant, it's a multiplier, and this multiplier is also known as the Lagrange multiplier, okay. So alpha is what is known as Lagrange multiplier. All right. So now what we are going to do for constraint restoration, obviously the same thing which we did last time, that is to say this objective function j f hat we are going to differentiate with respect to f hat, all right, and equate that to a zero vector, all right. So by setting delta j f hat del f hat equal to 0, we are going to get 2 q transpose q f hat minus 2 alpha h transpose g minus h f hat. All right, this is what we are getting, and from this equation, okay, we can solve for f hat, okay, under the minimized case, and look what f hat we get. So by solving this, by solving the above, we get f hat equals h transpose h, okay, plus I write another constant gamma. Gamma is nothing but, gamma is defined as 1 upon alpha. So in place of writing as 1 upon alpha, I am writing gamma. So h transpose h plus gamma q transpose q, this entire thing which is written within this parenthesis, inverse h transpose g. All right, this is what you are going to get as a solution of f hat, okay, in terms of the matrices, okay. You know what H is, okay. H is nothing but the, again I repeat, it's the block circulant matrix obtained from the impulse response of the degradation model, and Q is nothing but a linear operator of our choice, all right, and G is the given degraded image from which we are estimating this f hat, all right. So this is this is going to be an important relation, okay, which we will make use of, okay, in our next part of discussion. We will make use of this equation. It's a very important one. Let us call this equation, okay, as equation number 1, okay, and the other equation which we had got, okay, so this is the equation we are getting for constrained restoration, and for unconstrained what we got was very simple. We had obtained f hat equal to simply H inverse G. Okay, this was equation number, this we are calling as equation number 2. Now if we proceed with equation number 2, we know what we will get. We will get the inverse filter, okay, and this we already discussed, and we will now proceed in the lines of equation 1, okay. We will see that what kind of choice are we going to do for this Q transpose Q, okay, and a particular choice of this Q transpose Q, okay, implements what is known as a Weiner filter, okay. So how to choose this Q transpose Q, that discussion I am postponing little while, okay. So that will be discussed when we discuss the details of the Weiner filtering approach. But before beginning Weiner filter approach, let me tell you what the essence of that approach is. Again, in this filtering approach, Weiner filtering approach, okay, it is not based on the restoration of a single image alone. Rather, it is a restoration technique which makes use of an ensemble of images. And why ensemble? Because again, this restoration heavily makes use of the image correlations. All right. So we have to consider the correlation functions of the image as well as the correlation functions of the noise, okay, and using those correlation matrices, okay, we will define this Q transpose Q. All right. Sorry, I have to write all these things in terms of the matrices and vectors. So this is what we will get. All right. So we will now define the correlation matrices, okay, for F as well as for N. All right. So let us define the correlation matrix for F. F means the undegraded image. I mean the undegraded image I am denoting by the vector F. All right. So RF, okay, the correlation matrix F. Supposing F, if F is of size N, okay, then what should be the size of RF, the correlation matrix? N by N, okay. And what is going to be the definition of the correlation matrix? You remember we had defined the correlation matrix during our transform techniques, okay, while discussing the image transforms we had discussed the correlation matrix. It is simply given by the expectation of what? You remember? It is the expectation of F transpose, okay. And very similarly the correlation matrix for the noise N is defined as Rn as the expectation of N vector product N transpose, okay, where E is nothing but the expectation operator. Now how do you get the ijth element of any matrix, say Rf? So if you want to get the ijth element of Rf, okay, ijth element is nothing but a scalar quantity. Ijth element of Rf is going to be equal to, can you tell me, is expectation of so we can call that as Fi and Fi Fj, okay, where Fi is the ith element of F vector, Fj is the jth element of F vector. I am not writing this in vector because these are elements. Fi Fj's happen to be the elements, so the ijth element of Rf is equal to expectation of Fi Fj. All right. Now, this correlation is obviously for images, this correlation is going to be, is it real or complex? Has to be real. Okay. Now, if I consider the jith element of RF, what is it going to be? Again, expectation of fj fi. Okay. So, if I consider this, we will get expectation of fj fi. Okay. Again, this is also going to be a real. And what it is going to be? Aren't both the things same? So, expectation, if we are talking of expectation of fi, fj, that must be same as expectation of fj, fi. Very much obvious. Very similarly, expectation of ni, nj is going to be same as expectation of nj, ni. Does it lead to any interesting property of the correlation matrices? Yes, somebody has already given the answer. It is, RF and Rn, they are going to be real and symmetric matrices. Well, these are very important. So, both RF and Rn are real and symmetric. Alright? Now what else is there? Okay? About the image. Okay? What other interesting properties we can extract? Well, how do we measure the correlation? The correlation, or rather, let us study the nature of these matrices. Obviously, elements of RF indicates correlation between, or rather ijth element of RF indicates the correlation between ith element of F and jth element of F. Alright. Now, if the ith element and jth element, they happen to be very close to each other, then what do you expect? The correlation measure high or low? Yes, if ith element and jth element, they happen to be very close to each other, then obviously correlation measure is going to be high. If I is equal to j, what do you expect? A perfect correlation. Okay, because it's the correlation of the pixel with itself. Okay, so obviously this is going to give rise to high correlation, or rather if you are taking the normalized correlation, it's going to be equal to 1. But if you are considering I and j to be widely different from each other, what will it lead to? Correlation is going to be small. Okay, so physically it means like this. If you have an image like this, okay, considering the correlation between this element and this element, these two elements, they are going to be quite high correlation. But if I am considering correlation of this element with this element, the correlation is obviously going to be small. Okay, because this pixel and this pixel are much distant apart. Alright? Now, as a result of this, okay, what should be the characteristic of this RF and Rn matrix? Firstly, let us study what is going to be the diagonal elements. The diagonal elements will indicate 1. Okay, the diagonal elements will be high in value. Okay, so the diagonal elements will be obviously 1. The elements which are close to the diagonal elements, okay, what do they physically interpret? What do they physically represent? They represent closer pixels, pixels whose distances are less. Okay, their correlation is also going to be high. So obviously the matrix nature will be like this. If you are writing the matrix in this form, okay, diagonals will be obviously non-zero elements, and the elements which are quite close to the diagonals, okay, maybe in this band, whatever elements are there, they also will be non-zero. Okay, but the elements which are there on the upper right corner and the elements which are there in the bottom left corner, they are going to be very small, possibly 0. Okay, and generally it is found that if the distance exceeds, if the distance between the ith pixel and the jth pixel exceeds 20 to 30 pixels, okay, for all practical purposes, RF can be considered to be 0. Okay, actually a very similar situation is also coming for Rn. Okay, so what happens here? You will get 0 elements. Here you will get 0 elements, but only in the diagonal, and some elements which are within a band closer to the diagonal, they are going to be non-zero elements. So that is going to be the composition of the RF and Rn matrices. Okay, so that is also one property which we very much know. Now I am going to derive yet another very interesting property. Okay, all right, before I derive that, I have to make one assumption. Supposing this is the image and you assume that the image is periodically folded over, in the sense that if this is the image, okay, and if this is the, I mean this is the first column, this is the last column, and if you are considering any column beyond the last column, okay, don't consider it to be 0. Assume that the same image repeats itself. Okay, that is to say the first element, the first column becomes the n plus 1th column, and again similarly first row becomes the n plus 1th row. Okay, so all over the place, if you consider the image function to be periodic, that means to say you consider as if to say the entire image is folded over in both x direction as well as in y direction. Okay, I am going to make that assumption, and mind you, making that assumption is not absolutely I mean out of any basis, because whenever we are considering the frequency domain of any image, okay, what we are after all doing, I mean if the moment we are considering the discrete Fourier transform of something, okay, the discrete Fourier transform outputs, rather in the transform domain it becomes periodic, and not only that, because of sampling in the I mean original image domain or sampling in the spatial domain, even the spatial domain samples will be assumed to be periodic. Okay, so this periodicity both in the spatial domain as well as in the transform domain you are anyway assuming in discrete Fourier transform. So assume a periodicity in the discrete domain, I mean in the spatial domain, and using this assumption, now try to think over what are going to be the elements of these correlation matrices. Again, I told you that the best measure of correlation matrix is when the distance is least, that means to say for the diagonal elements. Okay, and as you go away from diagonals, the correlation is going to decrease, and it is not, the value of the correlation is not dependent upon the position of the pixel, rather it is only dependent upon the distance between ith and jth pixel, not on the location of ith and jth, but on the distance between ith pixel and jth pixel. Alright, so can anybody tell me that what does it lead to?
Symmetrical this correlation function also.
No, symmetrical we have already decided. Periodic, yes, periodicity in which sense? Try to recollect. Yes, exactly. That is the answer, that even this RF and Rn matrices, they are going to be circulant matrices. Okay? If you are considering that in the two-dimensional sense, it's going to be block circulant matrices. This is exactly what we are getting, isn't it so? Okay? For the benefit of those who did not get this immediately, let me tell you why. The correlation measure for the first row, the correlation measure is highest over here, and here, I mean, so supposing the correlation measure for this is 1, and this is D1, this is D2, this is D3, I mean, like this, it is decreasing. For the second row, okay, this for the correlation between the second element and the second element. So this is the first element, second element, third element, fourth element, like this. Okay, correlation of that with the first element. All right, let me redraw the matrix. Okay, how we are composing the correlation. This is the first row, second row, third row, etc., etc. Okay, let us say row number 0, 1, etc., etc., up to row number n minus 1. And this is again column number 0, 1, etc., etc., up to column number n minus 1. And I am having n number of, capital N number of elements, okay, in the image. Now, the correlation between 0th pixel and 0th pixel going to be the highest, 1. Correlation between the first pixel and first pixel going to be 1. Correlation of n minus 1th pixel and n minus pixel 1. So all the diagonals are becoming 1. Second thing, the correlation between 0 and 1th pixel is going to be some measure, let's say D. D1. 0 and 2, it's going to be D2. Like this. Whenever I am considering the correlation between the 1th element and the second element over here, the distance is going to be unity. And for unit distance, the correlation measure is going to be D1. This is going to be D2, etc., etc. Again, for the third row, 1 comes here, D1 goes here, D2 goes here, like this. Okay? And I wouldn't have got a circulant matrix in the strict sense if I had not assumed a periodicity in the spatial domain. But because of the fact that I have considered periodicity in the spatial domain, this entire row which I am considering, okay, this can be assumed to be circularly shifting. Okay, and I will get a circulant matrix, so it is a block circular matrix. So this is a very interesting property that I have got for the correlation matrix. Alright, now what is the advantage? Why did I formulate it into such a kind of block circulant matrix? Can you tell me what is going to be my ulterior purpose of doing that? I simply want to diagonalize these matrices, because I know how to diagonalize a block circulant matrix. I know how to diagonalize H. So since I know how to diagonalize H, I must know that how to diagonalize RF and how to diagonalize Rn. Alright. Now in the case of H, I was calling the diagonal matrix as D, and in the case of RF, okay, its equivalent diagonal matrix I am going to call as A, and for Rn, its equivalent diagonal matrix I am going to call as the matrix B. Alright. So let us see what does it lead to. So tell me what is going to be RF written in terms of the diagonalized matrix A. Quick. Pre multiplied by A, pre multiplied by W, and post multiplied by W. And what is going to be Rn? This is equal to, related to B, again pre multiplied by W, post multiplied by W inverse. Alright. And now, so we know that RF and Rn can be diagonalized just like the way H can be diagonalized into D. Okay. And by diagonalization, okay, what exact advantage did we get? What were the physical significance for the elements of D matrix? Try to recollect. If we are going over to the Fourier transform, then it was the DFT of the H matrix. Okay, DFT of the impulse response. So the elements of D was indicating the discrete Fourier transform of the impulse response. Okay, and very similarly, the elements of A matrix is going to be the discrete Fourier transform of the elements of this correlation matrix. B is going to be the discrete Fourier transform of the elements of Rn. Okay, and they are the correlation matrices. And as a matter of fact, the discrete Fourier transform of the correlation matrices elements, okay, they are what is known as the power spectral densities. Okay, this gives rise to the power spectral density. So A will indicate the power spectral density of the F function, and B will indicate, the diagonal elements of B will indicate the power spectral density of the noise term. Alright. Anyway, so this is what we are getting. And another thing which we should decide right now is, again, going over to the solution in the constraint case. Okay, this is the constraint solution of F hat, which we had obtained today morning only. F hat is equal to H transpose H plus gamma Q transpose Q inverse H T G. Alright, and we don't know what this Q transpose Q is going to be. Okay, now let us make a choice of this Q transpose Q. Okay, and what we will take now is define Q transpose, choose Q in such a manner that Q transpose Q becomes equal to RF inverse Rn. Okay, such that in place of Q transpose Q, I will be substituting RF inverse Rn in this equation number 1. So now I am going to rewrite equation number 1 by substituting RF inverse Rn in place of Q transpose Q. So what I will now write is F hat equals H transpose H plus gamma RF inverse Rn. This whole thing inverse H transpose G. H, right? Now what I would ask you to substitute is, substitute all the diagonalized relationships, all the diagonalization relation. You remember what was our H? H was equal to W D W inverse. In place of RF, substitute W A W inverse. In place of Rn, substitute W B W inverse. Okay, substitute this and do all the well-known matrix manipulations. Okay, if you do that, okay, if you are taking the inverse of this, then again in terms of matrix only, and in place of H we are going to write the, in place of RF Rn we are going to substitute this, and what you will get is this. So by these substitutions you will get F hat equal to W D star, the complex conjugate of D, D W inverse plus gamma W A inverse B W inverse. This entire thing written within the parenthesis inverse product W D star W inverse G. Alright, looks very complicated, but it will not remain as complicated. What we should do now? What did we do last time? For F hat, when we were representing F hat in terms of our D and G, okay, D, W and G, what did we do that time? We had gone over to the frequency domain. So now if we go over to the frequency domain, the relation will look much simpler. Okay, so what we will do, we will simply pre-multiply both the left hand side as well as the right hand side by W inverse. So what we will get in the process, W inverse F hat equals to d star d, okay, plus gamma A inverse B, okay, this whole thing inverse, d star inverse W, d star, sorry, W inverse G. Alright? And now try to interpret this thing physically. Okay? What is this W inverse F hat? Discrete Fourier transform of F. Okay? Of F hat rather. What is the significance of W inverse G? Again, discrete Fourier transform of G. Alright? And now the remaining terms, we know their individual physical significances. D indicates the discrete Fourier transform of the impulse response. A indicates the power spectral density of the F signal, okay, of the signal F. B indicates the power spectral density of the noise. Alright? So now, writing in terms of all these things, okay, we can write in place of, so how to compute the Fourier transform elements is like this. We can compute the kth element, we can compute the kth element of the degraded, of the estimated image, okay, estimated or rather the restored image, okay, its kth component in the frequency domain. This is in the frequency domain, equals, okay, from this relation possibly you will be able to tell me what is going to be this. Since this is an inverse term, okay, it will come in the denominator, okay, this will come in the denominator. And again, what is d star d's significance? It is going to be the mod of HKL square, where capital H indicates the, capital HKL indicates the frequency domain impulse response. Okay, so just I am going to write, and again you verify HKL mod HKL square, this indicates d star d, okay, plus gamma, again look at what it is, A inverse B. So A will come in the denominator term, and A indicates the power spectral density of the original signal. So that comes in the denominator, and let us call the power spectral density of the signal as S of F. Alright, with index KL. This goes in the denominator term, and what remains in the numerator term is S, let's call it as eta KL. Okay, S eta KL is the noise spectral density. This is the numerator is the noise spectral density, denominator is the signal spectral density. Alright, so this becomes the gamma A inverse B term. Okay, so I've got d star d plus gamma A inverse B. Since this was whole thing inverse, it has come in the denominator term. In the numerator term, what are we getting? D star. Okay, so obviously in place of D star, we will get H star KL. Okay, and then what else is remaining? W inverse G. What are we going to write there? Capital G KL, indicating that capital G is the Fourier transform. So KL is Fourier transform of the degraded signal, GKL. Alright. Now this expression is okay, but there is a term H star KL, so let us do something with it. What I can do is, if I bring out, if I multiply this thing by 1 upon HKL, then this HKL will go on top. Okay, multiplying the numerator as well as the denominator by H of KL, basically the numerator becomes HKL square, mod of HKL square, the numerator becomes, and in denominator we get the HKL term. So the same thing can be written as 1 upon H of KL, okay, and then this whole thing becomes mod of HKL square divided by HKL square mod plus gamma S eta KL by SF KL, okay. This whole thing I write within a parenthesis multiplied by G of KL, okay, and this will be varied for which KL? Both K and L will vary from 0 to n minus 1. We have assumed an image with m equal to n, alright. So with that, this is how we will be computing the KLth element, right? Now study this equation that we have got in the frequency domain. Let us say that the noise term is absent. That is to say, the noise power spectrum density is equal to 0. At all KL, we assume that S eta KL is equal to 0. Then what do you get from this expression? GKL by HKL. So F hat KL becomes GKL by HKL. What does it mean?
Noise.
Inverse filtering. This was our popular inverse filtering. So that means to say, where we have deviated from the inverse filtering, we have only introduced the noise spectral density also in this term. Alright, so that is where we had a major deviation. But so far I haven't talked anything about this gamma. Alright, so what we were considering first is gamma equal to 0. Gamma is equal to 0 leads to inverse filtering. And if gamma is chosen to be equal to 1, okay, then the filtering which we are doing within this entire thing written within this parenthesis, that filter is called as Weiner filter. Okay, so when gamma is equal to 1, okay, this entire expression is called as the filtering is called Weiner filtering. All right, but do you think that it is really optimal? Well, again, going back to our objective function definition and that minimization expression, all right, look at this. What did we decide when we had formulated this equation number 1? We had said that we will be choosing the gamma such that this is minimized. Okay, now we are permanently keeping gamma equal to 1, so it is not optimal. All right, so if we can make gamma variable, okay, then possibly we can lead to an optimization. So if we have gamma as a variable, okay, then this filtering is called as, so if gamma is variable, we call it as parametric Weiner filter. All right, now there is one more $1 million question over here. Go over to our expression for F hat KL. Okay, It is good to have this equation, but what are the things that you need to know? You need to have a very good idea about, not only the degradation model, H of KL you must know. Unless you know the degradation model, you can't do the restoration, so H of KL must be known. That goes without saying. But you must also know SF KL, you must also know S eta KL, the power spectral density of the signal as well as the noise. Okay? And not only that, how do you measure this? This must be measured over an ensemble of images. So what we should rather do is that, now in many of the cases, in many practical cases, okay, wherever we are given single images or wherever no clue is available as to what this SF and what this S etas are going to be, okay, in absence of any such clues, many a times for simple implementation, people take this gamma S eta KL divided by SF KL to be a constant quantity. Call it any constant quantity K, okay, so that what you have in this entire expression is only expression involving H of KL, which is known to you. Alright, and then you can have F hat of KL. So if you substitute a constant K in place of gamma S eta K alpha divided by SF K alpha, what you get is F hat of KL equals 1 upon H of KL multiplied by mod of H of KL square divided by mod of H of KL square plus that constant K, okay, and obviously this whole thing multiplied by what? GKL. So GKL is given to us, rather G of Mn is given to us in the spatial domain. We can compute GKL. The impulse response of the degradation model, you assume that the point spread function or rather the impulse response is known to you. So you know what that impulse response is going to be in the frequency domain. Okay, so the frequency domain coefficients of the impulse response and this frequency domain coefficients of the degraded image, if those are known to you, you can compute the frequency domain coefficients of the restored image. Now you take the Fourier inverse for this entire thing, or rather Fourier inverse of this whole expression. What you will get is the restored image. Alright. Now in the next class we will be considering some other restoration approach which is known as the constraint least square restoration approach, in which instead of taking an ensemble of images, okay, also do the restoration using single images. Okay, we will see how to do that in the constraint restoration. Okay. Any questions? Thank you.